So once again, we said that this has an initial velocity, which means it has an initial kinetic energy. So then that kinetic energy divided by the charge should give me the electric potential, the maximum electric potential that it can reach. Okay, because it can't go farther than that. If it could, it would have a higher one. So I don't know, what does that come out to be? Well, let's see. The mass of a proton is 1.6 times 10 to the minus 27 kilograms. Okay, and so that's 1/2 times that, so that's 0.8 times 10 to the minus 27 times v squared. V squared is 4 times 10 to the 10, so 0.8 times 4 is 32 times 10 to the minus 27, and 10 makes minus 17. 1/2 mv squared. So something like that?
Yes.
What is anybody doing this on a calculator while I'm talking? I mean, I got something like 3.2 times 10 to the minus 17 joules. Is that right?
You're going too fast.
Oh, you got it too, or you're just probably completely off. I know. What did Alan or Patrick get? Oh, okay. So I was a little bit off.
Wow, thanks.
Times 10 to the minus 17 joules over the charge was 1.6 times 10 to the minus 19 coulombs. So this is about 200 volts, give or take a volt. See, that was my birthday.
Standards just broken.
So what? There's absolutely no evidence of me doing anything broken at all.
We have witnesses.
All right. Wait, are any of you 18? Oh, fuck. I was gonna say, if you're not 18, your testimony can be destroyed. But anyways, so this is 200 volts. That's how you can say without a doubt that it never reaches the thing. Okay, so sorry. I'm trying to think in my mind, like, how do I know if it says mid-range capacitor? So that means this original potential is like 250, right? And then so this got added, but it wasn't enough to meet over there. And then so when this drops back here, it's essentially this kinetic energy is going to equal the 450. Okay, so all right, so here we calculated. Is this on? Okay, good. This is actually important because I didn't include this in the beginning. Everybody was okay with how we got 200. Right? Okay. Does it make sense to you that 200 volts is not where this started? Or we're not sure because it's somewhere in between the plates. If we shot this proton from zero out, does it make sense to you that it would stop at 200 volts? Does that make sense to you? Okay. So what we calculated was delta V. True? So we needed to know what was the original V. So what was the V0 or V? Wow, great. That looks like this. Okay. What was the electric potential initial? Now they told us that it was halfway between, which means the initial electric potential is 250 volts. So we know that it didn't hit only if we add this delta V to the original V. So the point that it got to was 450 volts. So it almost hit it, but not enough. Yeah, it was 50 volts shy. Does that make sense? Okay, good. And then that makes this one very easy. Where? When it's over? Yes, this was 0 volts. what they're telling us is, and again, I apologize for not reading the problem clearly. Once we know this, then we can just say that energy is conserved. So the initial mechanical energy is. I'm sorry. I should say whatever. Energy is conserved. And the initial energy is kinetic energy, and I'm just saying the energy is conserved. And the initial kinetic energy plus, I'm going to say, the electrical energy is going to equal the final kinetic energy. Right? And the electrical energy is going to be the 450 times the Q. Does that make sense? It's not Q1, Q2 over what? Yeah, this, no, I can do this, 1/2 mv squared, but then this is going to be 200 volts times Q plus, and that equals 1/2 mv final. Right? Or 450 volts times Q plus equals 1/2 mv final. Yeah, thank you. This is plus the 250 that it started off with. So if I use the original velocity kinetic energy plus the 250 where I started, then that's this. Or I could just say, go from 450 where I knew it was 2 and